Hi and welcome to lecture 4.3 of the domain-specific languages of mathematics course. And I will talk about homomorphisms again. So we have already mentioned three individual predicates, h2, h1, and h0. They all talk about when a certain function h is a homomorphism from one operation to another, or from one set to another. So we have the first h2 here saying that little h is, which is a function from a to b, is a homomorphism from a capital operator to a lowercase operator if, well, for all x and y, if we apply h on the capital operator, we get the same result as applying h to the two components and then combining them with the lowercase operator. So as before, we're translating from the A world, when we have the operator inputting a's and returning a's, to the B world, when the operator is completely just talking about B values. As we've seen, we can also make a version of this for a unary operator, capital F and small f, and that then has just one for all quantification, but it still has the pattern of applying h after the big operator or before the small operator. And finally, the sort of nullary case, where we just have a constant or a value e, capital E, and a lowercase e. Then it's just no quantification, the sort of zero quantifications, and h applied to e should be equal to e. Still, we translate from the A world into the B world. This is all described in book section 4.2, and I will now go on to generalize this to homomorphisms between structures. So, one simple structure that we have been talking about indirectly is a monoid. I'll actually write that over right here, because so a monoid. So a monoid is a mathematical class, basically, if we talk Haskell speak, which has two operations, one binary and one nullary. So often the typical example of a monomorphism or of a monoid is natural numbers, addition, and zero. But we can also have those same natural numbers with multiplication and 1. So the rules of a monoid are just that we should have a value, in this case the first example 0, which acts as do nothing for the operator. So 0 plus x is equal to x, and similarly 1 times x is equal to x. So we've seen this, not calling it monoid in the previous lecture, but we called something of this shape additive and something of this shape multiplicative. But from the mathematical underlying point of view, they are the same. So now, what is a monoid homomorphism? So a structural homomorphism between monoids. Well, so I define here a predicate, monoid homomorphism, and it has three components. As usual, h, which is just a function from a to b still. And then I have this triple, which is often the notation for a monoid in the mathematical literature, which has the type and the operators on binary and unary, or nullary. And then the third component is the target, the type, and the operator of the binary and the element value, the nullary operator. So this predicate is defined in terms of my other predicates. So it just says that this function h, to be a monoid homomorphism, it should be an h2 and an h0. So the same h should take the capital op to smaller case op and capital E to lowercase e. And then we say that the function E is a monoid homomorphism from A to B, then clearly this is hiding some information, so often it's implicitly assumed that you know what the operator on A is and what the operator on B is. So if we have the example of the exponential function, it's a monoid homomorphism from addition to multiplication. Okay. So often we get a question like, does there exist a structure on the type B such that we have a monoid homomorphism from A to B, where we already know that A is a monoid? And this is something we've been actually doing several times this course already, even though we haven't had a terminology for it. But when we define a recursive function in the shape of a fold, then we have actually a structural homomorphism from the data type to the target type, to the semantic type. So all our evaluators so far have had this shape. So let's move one step further and do something more general. So in the general case, we have some age. I mean, the general case here, I mean the general case for evaluators, we have some syntax and we have some semantics, and we have age is an evaluator. So the structural homomorphism from this syntax to this semantics, where I've sort of done this mathematical abbreviation saying the syntax actually comes with some constructors and the semantics with some other semantic functions, but for brevity, this is the usual notation. So this is defined as there exist operators C1 to Cn. So I'm now assuming that there are n constructors in my data type in the syntax. And this is an AND with a big AND sort of from I equals 1 to n. So all of these little age predicates should hold. And notice the special case for the monoid, then I was from 1 to 2. There were two operators there. And then I've used A1 was 2 and A2 was 0. So the arity of the first operator, like plus, was 2, and the operator arity of the constant was 0. In each case, this same function age should take the constructor to the semantic function. And those should both have the same arity hi, which is a natural number for each I then. And if you write out the types to recognize this pattern, you see we have the age transforming us from the syntax world to the semantics world. We have a constructors, all of the constructors ci are purely in the syntactic world, taking as many arguments as indicated by its arity. And the corresponding semantic function ci is completely living in the semantic world. Its arguments and its result type is this sem, which the age returns. So this structure homomorphism predicate is just saying that there exists some function that satisfies some collection of functions ci that satisfies this. Okay, let's make that a little bit more concrete. Let's take a data type E, where we have an add constructor, a negate, so unary minus, and a 0. I would admit that this data type is not very interesting, because as you might imagine, if we have the usual algebraic laws for it, we can write minus 0, we can add 0 and minus 0 together and so on. We can actually know or get any other value than 0. But just to keep the example clean and simple here, we could certainly add other constructors later. This evaluator for this data type, I would claim, is the natural way of writing it, is saying, okay, add is translated to a lowercase add, negation to a lowercase negation, and 0 to some constant 0. So whatever these functions and semantic functions are, I mean, if this is addition for natural numbers, negation for natural numbers, and 0, or if it's for some more complicated structures like functions or function expressions, whatever they are, it will still satisfy the homomorphisms conditions. So if you remember, this first thing is basically the statement age2 of eval from add to add. I didn't have quite a space here. Similarly, this one is saying age1 of the same eval from neg to neg. And this last line is saying age0 eval from capital 0 to small 0. So that means that for all of the constructors of the data type, if this is the definition of the function, I do have the prerequisite parts of the definition of the structural homomorphism, the age2, the age1, and the age0. So whatever add, neg, and 0 I get, by definition, this eval function will be a structural homomorphism from E to my semantics. So it doesn't have to be sort of an interesting one, but it does do the right thing for this predicate to hold. I should mention a few more things about the logical form of the structural homomorphism here. If we want to prove that some function is not a homomorphism, then we need to try to negate this whole thing. So what does that mean? Well, we had to show not exists, which means that for all possible functions C1 to Cn, this is not the case. So we have to prove that for all constructor semantic functions, and then negate the for all quantification, or the and here. So negating the and becomes an or between not homomorphic. So it's enough to show that it's for all possible functions C1 to Cn, one of them sort of does not satisfy its part of the deal. And then each of those in turn have a for all quantification in them, and that means we only have to find one counterexample for one of them, in which case we have actually done in showing that something is not a structural homomorphism. And I mention this because there is a part of the second assignment for those taking the course where you need to prove that something is not a homomorphism. Okay, this was all for this part.